A multi-core processor is a single computing component with two or more independent actual central processing units, which are the units that read and execute program instructions. The instructions are ordinary CPU instructions such as add, move data, and branch, but the multiple cores can run multiple instructions at the same time, increasing overall speed for programs amenable to parallel computing. Manufacturers typically integrate the cores onto a single integrated circuit die, or onto multiple dies in a single chip package. Processors were originally developed with only one core. Multi-core processors were developed in the early 2000s by Intel, AMD and others. Multi-core processors may have 2 cores, 4 cores, 6 cores, 8 cores, 10 cores, or more. A multi-core processor implements multiprocessing in a single physical package. Designers may couple cores in a multi-core device tightly or loosely. For example, cores may or may not share caches, and they may implement message passing or shared memory intercore communication methods. Common network topologies to interconnect cores include bus, ring, two-dimensional mesh, and crossbar. Homogeneous multicore systems include only identical cores. Heterogeneous multicore systems have cores that are not identical. Just as with single processor systems, cores in multi-core systems may implement architectures such as superscalar, VLIW, vector processing, SIMD, or multithreading. Multi-core processors are widely used across many application domains including general-purpose, embedded, network, digital signal processing, and graphics. The improvement in performance gained by the use of a multi-core processor depends very much on the software algorithms used and their implementation. In particular, possible gains are limited by the fraction of the software that can be run in parallel simultaneously on multiple cores. This effect is described by Amdahl's law. In the best case, so-called embarrassingly parallel problems may realize speed-up factors near the number of cores, or even more if the problem is split up enough to fit within each core's cache, avoiding use of much slower main system memory. Most applications, however, are not accelerated so much unless programmers invest a prohibitive amount of effort in refactoring the whole problem. The parallelization of software is a significant ongoing topic of research. Terminology. The terms multi-core and dual-core most commonly refer to some sort of central processing unit, but are sometimes also applied to digital signal processors and system-on-a-chip. The terms are generally used only to refer to multi-core microprocessors that are manufactured on the same integrated circuit die. Separate microprocessor dies in the same package are generally referred to by another name, such as multi-chip module. This article uses the terms multi-core and dual-core for CPUs manufactured on the same integrated circuit, unless otherwise noted. In contrast to multi-core systems, the term multi-CPU refers to multiple physically separate processing units. The terms many-core and massively multi-core are sometimes used to describe multi-core architectures with an especially high number of cores. Some systems use many soft microprocessor cores placed on a single FPGA. Each core can be considered a semiconductor intellectual property core as well as a CPU core. Development. While manufacturing technology improves, reducing the size of individual gates, physical limits of semiconductor-based microelectronics have become a major design concern. These physical limitations can cause significant heat dissipation and data synchronization problems. Various other methods are used to improve CPU performance. Some instruction-level parallelism methods such as superscalar pipelining are suitable for many applications, but are inefficient for others that contain difficult-to-predict code. Many applications are better suited to thread-level parallelism methods, and multiple independent CPUs are commonly used to increase a system's overall TLP. A combination of increased available space and the demand for increased TLP led to the development of multi-core CPUs. Commercial incentives. Several business motives drive the development of multi-core architectures. For decades, it was possible to improve performance of a CPU by shrinking the area of the integrated circuit, which drove down the cost per device on the IC. Alternatively, for the same circuit area, More transistors could be utilized in the design, which increased functionality, especially for CISC architectures. Clock rates also increased by orders of magnitude in the decades of the late 20th century, from several megahertz in the 1980s to several gigahertz in the early 2000s. As the rate of clock speed improvement slowed, increased use of parallel computing in the form of multi-core processors has been pursued to improve overall processing performance. Multiple cores were used on the same CPU chip, which could then lead to better sales of CPU chips with 2 or more cores. Intel has produced a 48-core processor for research in cloud computing. Each core has an x86 architecture. Intel has loaded Linux on each core. Technical factors: since computer manufacturers have long implemented symmetric multiprocessing designs using discrete CPUs, the issues regarding implementing multi-core processor architecture and supporting it with software are well known. Additionally, utilizing a proven processing core design without architectural changes reduces design risk significantly. For general-purpose processors, much of the motivation for multi-core processors comes from greatly diminished gains in processor performance from increasing the operating frequency. This is due to 3 primary factors: the memory wall, the increasing gap between processor and memory speeds. This effect pushes cache sizes larger in order to mask the latency of memory. This helps only to the extent that memory bandwidth is not the bottleneck in performance. The ILP wall, the increasing difficulty of finding enough parallelism in a single instruction stream to keep a high-performance single-core processor busy. The power wall, the trend of consuming exponentially increasing power with each factorial increase of operating frequency. This increase can be mitigated by shrinking the processor by using smaller traces for the same logic. The power wall poses manufacturing, system design and deployment problems that have not been justified in the face of the diminished gains in performance due to the memory wall and ILP wall. In order to continue delivering regular performance improvements for general-purpose processors, manufacturers such as Intel and AMD have turned to multi-core designs, sacrificing lower manufacturing costs for higher performance in some applications and systems. Multi-core architectures are being developed, but so are the alternatives. An especially strong contender for established markets is the further integration of peripheral functions into the chip. Advantages: the proximity of multiple CPU cores on the same die allows the cache coherency circuitry to operate at a much higher clock rate than is possible if the signals have to travel off-chip. Combining equivalent CPUs on a single die significantly improves the performance of cache snoop operations. Put simply, this means that signals between different CPUs travel shorter distances, and therefore those signals degrade less. These higher quality signals allow more data to be sent in a given time period, since individual signals can be shorter and do not need to be repeated as often. Assuming that the die can physically fit into the package, multi-core CPU designs require much less printed circuit board space than do multi-chip SMP designs. Also, a dual-core processor uses slightly less power than 2 coupled single-core processors, principally because of the decreased power required to drive signals external to the chip. Furthermore, the cores share some circuitry, like the L2 cache and the interface to the front-side bus. In terms of competing technologies for the available silicon die area, multi-core design can make use of proven CPU core library designs and produce a product with lower risk of design error than devising a new wider core design. Also, adding more cache suffers from diminishing returns. Multi-core chips also allow higher performance at lower energy. This can be a big factor in mobile devices that operate on batteries. Since each and every core in multi-core is generally more energy efficient, the chip becomes more efficient than having a single large monolithic core. This allows higher performance with less energy. The challenge of writing parallel code clearly offsets this benefit. Disadvantages: maximizing the utilization of the computing resources provided by multi-core processors requires adjustments both to the operating system support and to existing application software. Also, the ability of multi-core processors to increase application performance depends on the use of multiple threads within applications. the situation is improving. For example, the Valve Corporation's Source Engine offers multi-core support, and Crytek has developed similar technologies for CryEngine 2, which powers their game, Crysis. Emergent game technologies Gamebryo Engine includes their Floodgate technology, which simplifies multi-core development across game platforms. In addition, Apple incorporated OS X, starting with Mac OS X Snow Leopard, and iOS starting with iOS 4, have a built-in multi-core facility called Grand Central Dispatch. Integration of a multi-core chip drives chip production yields down, and they are more difficult to manage thermally than lower-density single-chip designs. Intel has partially countered this first problem by creating its quad-core designs by combining two dual-core on a single die with a unified cache, hence any two working dual-core dies can be used, as opposed to producing 4 cores on a single die and requiring all 4 to work to produce a quad-core. From an architectural point of view, ultimately, single CPU designs may make better use of the silicon surface area than multiprocessing cores, so a development commitment to this architecture may carry the risk of obsolescence. Finally, raw processing power is not the only constraint on system performance. Two processing cores sharing the same system bus and memory bandwidth limits the real-world performance advantage. It has been claimed that if a single core is close to being memory bandwidth limited, then going to dual-core might give 30% to 70% improvement. If memory bandwidth is not a problem, then a 90% improvement can be expected. However, Amdahl's law makes this claim dubious. It would be possible for an application that used two CPUs to end up running faster on one dual-core if communication between the CPUs was the limiting factor, which would count as more than 100% improvement. Hardware trends. The general trend in processor development has moved from dual, tri, quad, hex, octo-core chips to ones with tens or even hundreds of cores. In addition, multi-core chips mixed with simultaneous multithreading, memory on chip, and special-purpose heterogeneous cores promise further performance and efficiency gains, especially in processing multimedia, recognition and networking applications. There is also a trend of improving energy efficiency by focusing on performance per watt with advanced fine-grain or ultra-fine-grain power management and dynamic voltage and frequency scaling. Architecture. The composition and balance of the cores in multi-core architecture show great variety. Some architectures use one core design repeated consistently, while others use a mixture of different cores, each optimized for a different, heterogeneous role. The article CPU Designers Debate Multi-Core Future by Rick Merritt, EE Times 2008, includes these comments. Chuck Moore suggested computers should be more like cell phones, using a variety of specialty cores to run modular software scheduled by a high-level applications programming interface. Atsushi Hasegawa, a senior chief engineer at Renesas, generally agreed. He suggested the cell phone's use of many specialty cores working in concert is a good model for future multi-core designs. Anand Agarwal, founder and chief executive of startup Tylera, took the opposing view. He said multi-core chips need to be homogeneous collections of general-purpose cores to keep the software model simple. Software impact. An outdated version of an antivirus application may create a new thread for a scan process, while its GUI thread waits for commands from the user. In such cases, a multi-core architecture is of little benefit for the application itself due to the single thread doing all the heavy lifting and the inability to balance the work evenly across multiple cores. Programming truly multi-threaded code often requires complex coordination of threads and can easily introduce subtle and difficult-to-find bugs due to the interweaving of processing on data shared between threads. Consequently, such code is much more difficult to debug than single-threaded code when it breaks. There has been a perceived lack of motivation for writing consumer-level threaded applications because of the relative rarity of consumer-level demand for maximum use of computer hardware. Although threaded applications incur little additional performance penalty on single-processor machines, the extra overhead of development has been difficult to justify due to the preponderance of single-processor machines. Also, Serial tasks like decoding the entropy encoding algorithms used in video codecs are impossible to parallelize because each result generated is used to help create the next result of the entropy decoding algorithm. Given the increasing emphasis on multi-core chip design, stemming from the grave thermal and power consumption problems posed by any further significant increase in processor clock speeds, the extent to which software can be multi-threaded to take advantage of these new chips is likely to be the single greatest constraint on computer performance in the future. If developers are unable to design software to fully exploit the resources provided by multiple cores, then they will ultimately reach an insurmountable performance ceiling. The telecommunications market had been one of the first that needed a new design of parallel data path packet processing because there was a very quick adoption of these multiple core processors for the data path and the control plane. These MPUs are going to replace the traditional network processors that were based on proprietary micro or pico code. Parallel programming techniques can benefit from multiple cores directly. Some existing parallel programming models such as Silk Plus, OpenMP, OpenHMPP, FastFlow, Scandium, MPI, and Erlang can be used on multi-core platforms. Intel introduced a new abstraction for C++ parallelism called TBB. Other research efforts include the CodePlay Civ system, Cray's Chapel, Sun's Fortress, and IBM's X10. Multi-core processing has also affected the ability of modern computational software development. Developers programming in newer languages might find that their modern languages do not support multi-core functionality. This then requires the use of numerical libraries to access code written in languages like C and Fortran, which perform math computations faster than newer languages like C. Intel's MKL and AMD's ACML are written in these native languages and take advantage of multi-core processing. Balancing the application workload across processors can be problematic, especially if they have different performance characteristics. There are different conceptual models to deal with a problem, for example using a coordination language and program building blocks. Each block can have a different native implementation for each processor type. Users simply program using these abstractions and an intelligent compiler chooses the best implementation based on the context. Managing concurrency acquires a central role in developing parallel applications. The basic steps in designing parallel applications are, partitioning. The partitioning stage of a design is intended to expose opportunities for parallel execution. Hence, the focus is on defining a large number of small tasks in order to yield what is termed a fine-grained decomposition of a problem. Communication. The tasks generated by a partition are intended to execute concurrently but cannot, in general, execute independently. The computation to be performed in one task will typically require data associated with another task. Data must then be transferred between tasks so as to allow computation to proceed. This information flow is specified in the communication phase of a design. Agglomeration. In the third stage, development moves from the abstract toward the concrete. Developers revisit decisions made in the partitioning and communication phases with a view to obtaining an algorithm that will execute efficiently on some class of parallel computer. In particular, developers consider whether it is useful to combine, or agglomerate, tasks identified by the partitioning phase, so as to provide a smaller number of tasks, each of greater size. They also determine whether it is worthwhile to replicate data and computation. Mapping. In the fourth and final stage of the design of parallel algorithms, the developers specify where each task is to execute. This mapping problem does not arise on uniprocessors or on shared memory computers that provide automatic task scheduling. On the other hand, on the server side, multi-core processors are ideal because they allow many users to connect to a site simultaneously and have independent threads of execution. This allows for web servers and application servers that have much better throughput. Licensing. Some software may be licensed per processor. This gives rise to an ambiguity, because a processor may be either a core or a combination of cores. Microsoft has stated that it would treat a socket as a single processor. Oracle counts an AMD X2 or Intel dual-core CPU as a single processor but has other numbers for other types, especially for processors with more than 2 cores. Embedded applications. Embedded computing operates in an area of processor technology distinct from that of mainstream PCs. The same technological drivers towards multicore apply here too. Indeed, in many cases the application is a natural fit for multicore technologies, if the task can easily be partitioned between the different processors. In addition, embedded software is typically developed for a specific hardware release, making misuse of software portability, legacy code or supporting independent developers less critical than is the case for PC or enterprise computing. As a result, it is easier for developers to adopt new technologies, and as a result there is a greater variety of multi-core processing architectures and suppliers. As of 2010, multi-core network processing devices have become mainstream, with companies such as Freescale Semiconductor, Cavium Networks, Wintegra and Broadcom all manufacturing products with 8 processors. For the system developer, a key challenge is how to exploit all the cores in these devices to achieve maximum networking performance at the system level, despite the performance limitations inherent in an SMP operating system. To address this issue, companies such as 6Win provide portable packet processing software designed so that the networking data plane runs in a fast path environment outside the OS, while retaining full compatibility with standard OS APIs. In digital signal processing the same trend applies. Texas Instruments has the 3-core TMS-320C6488 and 4-core TMS-320C5441, Freescale the 4-core MSC8144 and 6-core MSC8156. Newer entries include the Storm 1 family from Stream processors, incorporated with 40 and 80 general-purpose ALUs per chip, all programmable, and C as a SIMD engine and PI-kit with 300 processors on a single die, focused on communication applications. Hardware examples: commercial, adaptive Epiphany, a many-core processor architecture with up to 4096 processors on chip, Aeroflex Garisela Leon 3, a multi-core SPARC that also exists in a fault-tolerant version. Agile PhysX, a multi-core physics processing unit. Embrick M2045, a 336-core massively parallel processor array, AMD, A-series, dual, triple, and quad-core of accelerated processor units. Athlon 64, Athlon 64FX and Athlon 64X2 family, dual-core desktop processors. Athlon 2, dual, triple, and quad-core desktop processors. FX series, quad, 6, and 8-core desktop processors. Opteron, dual, quad, 6, 8, 12, and 16-core server workstation processors. Phenom, dual, triple, and quad-core processors. Phenom II, dual, triple, quad, and 6-core desktop processors. Sempron X2, dual-core entry-level processors. Turion 64X2, dual-core laptop processors. Radeon and Firestream multi-core GPU. Analog devices: Blackfin BF561, a symmetrical dual-core processor. ARM MPCORE is a fully synthesizable multi-core container for ARM11 MPCORE and ARM Cortex-A9 MPCORE processor cores, intended for high-performance embedded and entertainment applications. ASOCS Modem X, up to 128 cores. Wireless applications. Azul Systems, Vega 1, a 24-core processor, released in 2005. Vega 2, a 48-core processor, released in 2006. Vega 3, a 54-core processor, released in 2008. Broadcom Seabyte SB1250, SB1255 and SB1455. ClearSpeed, CSX700. 192-core processor, released in 2008. Cradle Technologies Court 3400 and Connecticut 3600, both multi-core DSPs. Cavium Networks Octron, a 16-core MIPS MPU. Freescale Semiconductor Core IQ series processors, up to 8 cores, Power Architecture MPU. Hewlett-Packard PA8800 and PA8900. dual-core PA RISC processors. IBM, POWER4, a dual-core processor, released in 2001. POWER5, a dual-core processor, released in 2004. POWER6, a dual-core processor, released in 2007. POWER7, a 4, 6, 8-core processor, released in 2010. POWER8, a 12-core processor, released in 2013. PowerPC 970MP, a dual-core processor, used in the Apple Power Mac G5. Xenon, a triple-core, SMT-capable, PowerPC microprocessor used in the Microsoft Xbox 360 game console. Kawi, MPPA 256, 256-core processor, released 2012, 32/64-bit IEEE 754 compliant FPU. Sony Toshiba's Cell processor, a 9-core processor with one general-purpose PowerPC core and 8 specialized SPUs optimized for vector operations used in the Sony PlayStation 3, Infineon Danube, a dual-core, MIPS-based, home gateway processor. Intel, Atom, single and dual-core processors for netbook systems. Celeron dual-core, the first dual-core processor for the budget entry-level market. Core Duo, a dual-core processor. Core 2 Duo, a dual-core processor. Core 2 Quad, 2 dual-core dies packaged in a multi-chip module. Core i3, Core i5 and Core i7, a family of multi-core processors, the successor of the Core 2 Duo and the Core 2 Quad. Itanium 2, a dual-core processor. Pentium D, 2 single-core dies packaged in a multi-chip module. Pentium Extreme Edition, 2 single-core dies packaged in a multi-chip module. Pentium Dual-Core, a dual-core processor. Teraflops Research Chip, a 3.16 GHz, 80-core processor prototype, which the company originally stated would be released by 2011. Xeon Dual, Quad, 6, 8, 10 and 15-core processors. Xeon 557-core, 60-core and 61-core processors. Intellisys, Seaforth 40C18, a 40-core processor, Seaforth 24, a 24-core processor designed by Charles H. Moore. NetLogic Microsystems, XLP, a 32-core, quad-threaded MIPS64 processor, XLR, an 8-core, quad-threaded MIPS64 processor, XLS, an 8-core, quad-threaded MIPS64 processor. NVIDIA, GeForce 9 multi-core GPU, GeForce 200 multi-core GPU, Tesla multi-core GPU. Parallax Propeller P8X32, an 8-core microcontroller. PicoChip PC200 Series 200 Euro 300 cores per device for DSP and wireless, Plurality HAL Series tightly coupled 16 to 256 cores, L1 shared memory, hardware synchronized processor. Rapport Killer-Core KC256, a 257-core microcontroller with a PowerPC core and 256 8-bit processing elements. C-Cortex Node has 6 MIPS64 cores on a single chip. Sun Microsystems, MAJC5200, 2-core VLIW processor, UltraSpark 4 and UltraSpark 4 Plus, dual-core processors. UltraSpark T1, an 8-core, 32-thread processor. UltraSpark T2, an 8-core, 64 concurrent thread processor. UltraSpark T3, a 16-core, 128 concurrent thread processor. SPARC T4, an 8-core, 64 concurrent thread processor. SPARC T5, a 16-core, 128 concurrent thread processor. Texas Instruments, TMS-320C80MVP, a 5-core multimedia video processor. TMS-320 TMS-320C66, 2, 4, 8-core DSP. Tylera, TILE64, a 64-core 32-bit processor, TILE-GX, a 72-core 64-bit processor. XMOS software-defined silicon quad-core XS1 G4, free, OpenSpark, academic, MIT, 16-core raw processor, University of California, Davis, asynchronous array of simple processors, 36-core 610 MHz as AP, 167-core 1.2 GHz as AP2. University of Washington, wave scalar processor, University of Texas, Austin, TRIPS processor, linker paragraph ping University, Sweden, ePuma processor. Notes: digital signal processors have utilized multi-core architectures for much longer than high-end general-purpose processors. A typical example of a DSP-specific implementation would be a combination of a RISC CPU and a DSP MPU. This allows for the design of products that require a general-purpose processor for user interfaces and a DSP for real-time data processing. This type of design is common in mobile phones. In other applications, a growing number of companies have developed multi-core DSPs with very large numbers of processors. Two types of operating systems are able to utilize a dual CPU multiprocessor, partitioned multiprocessing and symmetric multiprocessing. In a partitioned architecture, each CPU boots into separate segments of physical memory and operate independently. In an SMPOS, processors work in a shared space, executing threads within the OS independently. See also. References. External links: Embedded moves to multicore, Multicore news blog, IEEE, Multicore is bad news for supercomputers.